Welcome to the Lachesis program. First off, our choice of indicators. Since many countries are located near water bodies, many countries are susceptible to rising sea levels, floods, and tsunamis, which are becoming more common today due to climate change. Climate change also causes rising sea levels. This is due to heat expansion of water and to the melting of glaciers. The rising sea levels due to climate change not only make land uninhabitable, but also make land economically unviable. Rising sea levels also increases the risk of flooding. In fact, the percentage of the population exposed to flooding has increased globally, and floods have also become a lot more common. Floods have many negative impacts, from economic losses and fatalities to reducing access to clean water. Of course, climate change can also cause other natural disasters relating to oceans, like tsunamis and storm surges, both of which can kill many people. To recap, our motivation is that rising sea levels and natural disasters are becoming more common and have a significant negative impact. Hence, we aim to predict natural disasters and project possible sea level rises so that we can aid countries in evacuating citizens, preparing necessary defenses, and reducing casualties. Our method is by measuring sea levels, sea surface temperature, and melting glaciers. At this point, you might be wondering, how does measuring these indicators help us to achieve our aim? To answer that, we have to look at specific indicators. On sea level data can be used to create contour maps of sea levels. From these maps, scientists can determine speed and the direction of currents. Where the contours are steepest, the currents will be strongest. A strong current in the middle of the ocean might be caused by earthquakes and might cause flooding further inland. However, these maps take a very long time to create. Having more satellites helps in detecting sea levels, and this reduces the time taken for creation of these contour maps. On the melting of glaciers, studying the melting of glaciers helps us to better understand the cause of rising sea levels. We can also spot glacial lake outbursts and prepare necessary defenses. On sea surface temperature, rising sea surface temperature raises the risk of cyclones, which increases the threat of storm surges and flooding. Understanding sea surface temperature can help us to understand which regions are more vulnerable to cyclones. Sea surface temperature has also been used to improve flood modeling. Moving on, most of climate change's effects are due to global warming. The Earth radiation budget measures incoming energy from the sun and outgoing energy from the Earth. Studying it helps us to better track each country or region's energy absorption from the sun. This enables governments to better plan policies to reduce energy absorption, such as by reducing greenhouse gas emissions, thereby helping to slow climate change. In summary, by using satellites to measure these 4 indicators, we plan to help stop climate change and prepare against natural disasters.
With our interpretation and assessment of climate change, how will our design satellite combat such a severe problem? Introducing the Lachesis satellite program. The name Lachesis seeks to remind us that how we address climate change today will determine how much it will impact us tomorrow. Our Lachesis program aims to provide satellites capable of consistently measuring all of the variables listed with high precision, state-of-the-art instruments which provide accurate results with wide coverage through the use of a constellation of 3 satellites. Our first satellite, the Lachesis 1, will be equipped with an Earth Outgoing Radiometer, EOR, a Rapid Surface Altimeter in the Ku band, RSA-Ku, and a Rapid Surface Altimeter in the Ka band, RSA-Ka. Our first sensor is our Earth Outgoing Radiometer. This sensor contributes to tracking the Earth radiation budget. Though the Earth radiation budget is determined by both solar irradiance and outgoing radiation, solar irradiance is currently well tracked by systems on ISS providing accurate real-time data. This has led to modern Earth radiation budget trackers to focus on tracking outgoing radiation, which has not yet been well monitored. We have decided to implement 3 radiometers: a shortwave radiometer, a longwave radiometer, and a total radius radiometer. This will allow us to gain comprehensive information on the nature of the radiation coming from the Earth, and yields us better accuracy in our measurements by integrating results. Our second and third sensors both measure sea levels. Sea level altimeters are well established and backed by long heritage, but there exists a choice in spectral radiation band that is used to scan the sea surface. The options are Ka and Ku band altimeters. Ka band altimeters possess numerous advantages over Ku band ones, the most important one being the ability to provide more accurate vertical measurements of the sea surface. However, their major downside is that data in areas of heavy rain is unusable, while Ku remains reliable. We chose to design our primary sensor RSA-Ka as a Ka band altimeter, as areas of heavy rain are relatively uncommon, and our project has a huge focus on accurate measurements of sea levels. However, in order to provide consistent coverage, we also included a Ku band altimeter RSA-Ku on the Lachesis 1. Lachesis 2 will be equipped with RSA-Ka and an Ocean Dwell Wave Radiometer, ODR. Our Ocean Dwell Wave Radiometer utilizes both passive microwave and infrared radiometry to determine sea temperatures. The latter is more accurate and backed by stronger heritage, but is blocked by clouds. By integrating both systems, we hope to leverage cutting-edge technology to produce a more accurate data product that is also less subject to atmospheric interference. Lachesis 3 will be equipped with RSA-Ka and a glacial topographical radar. Our glacial topographical radar also involved the choice of equipment. Both synthetic aperture radar and optical images are established technologies. Though optical images provide better mapping of topographical features, they lack the agility and 24/7 reliable mapping through clouded and snowy areas that synthetic apertures provide, which is especially critical in glacial areas. So we have designed our glacial topographical scanner as an SAR providing cutting-edge imagery.
Now that we have gone through how the insides of our satellites work, let's talk about how we can actually get them up into space. Our chosen orbit is a 500 km Sun-Synchronous Orbit, or SSO for short, which is a standard orbit used by many previous weather missions such as the French-Belgian SPOT and the European ENVISAT satellites. The SSO is a near-polar orbit which ensures that the satellite moves over a specific area at the same local time, every time. This allows for a relatively constant sunlight angle on the ground each time it is being observed, and for our spacecraft to continuously get sunlight for energy without being blocked by the Earth. We have chosen a low Earth orbit of 500 km because, number one, it allows us to see the surface closer without needing as large a telescope, and number two, we can easily deorbit the spacecraft without using too much fuel at the end of the mission. Which brings us to the next point. Why deorbit the satellites? The answer is space debris. Space debris is basically just used rocket parts or spacecraft that are not in use, flying in orbit around Earth dangerously fast. In fact, fast enough to puncture or even destroy a spacecraft. The problem of space debris is very serious, as we have an estimated 130 million pieces of space debris in orbit, with many of them being too small to be tracked. If it continues increasing, we may face a situation where there is enough debris to create a long chain collision, essentially filling the orbits completely with small but deadly pieces of trash. This is also known as Kessler's syndrome. Part of the problem is satellites not using up their stored energy, for example in batteries, which can cause explosions if these areas are hit by space debris. Thus, we will both set a decay orbit into the atmosphere at the end of our mission and carry out passivation, which is the depletion of all stored energy on board. This is in accordance with guidelines proposed by governmental and intergovernmental agencies, as can be seen on screen. Now, to actually bringing our satellites into space. Since we are a relatively small private space company based in Singapore, it is not exactly viable for us to develop an entire rocket program and build a launch site just so we can get into space. So why not just get other companies to do it for us? Since our satellites are pretty small, they can be launched via the commercial hosted payload programs, where we can get rocket companies to launch multiple satellites for us. The image on screen is of an actual satellite mission, launched on a Falcon 9 rocket. We have identified SpaceX's rideshare program as being the most cost-effective hosted payload service, with the launch costing only $3.6 million for all 3 of our satellites, compared to other organizations which can go up to 20 or 30 million. This essentially saves a lot of money and the risk in developing a rocket program, allowing us to invest more money into the satellites themselves instead of focusing too much on the launch systems.
Now that we've covered the operational overview of our mission, let's go into a little more detail with regards to the engineering considerations. In other words, how do we ensure that our ship does not explode, implode, overheat, or run out of battery? We broadly divide our considerations into 3 categories: electrical, structural, and thermal. First, electricity. Due to the SSO, we can implement solar arrays to generate energy. We use a fold-out array design, which allows the fragile solar array to be held intact during launch. Backup energy supply is stored as rotational energy using a small flywheel system, which is shown to be more effective than chemical batteries, especially under low temperature conditions. Next, we consider the structure and temperature balance simultaneously. This is necessary as they are both affected by geometric considerations, and hence we have to solve a minimization for both cost and mass of materials at the same time. We do this by using a simplified analytical model. We first model the structure as a set of rectangular supports connected by truss beams and radiation plates, and by applying a buckling analysis to them. The satellite is then divided into a hot region and a cold region, separated by insulators, and the thermal balance equations with all the radiation terms from the sun reflecting off the Earth, and from radiation from the Earth itself, as well as power dissipating away from the satellite, and the conduction terms between the cold and the hot regions. These are all solved as an analytic model. These equations leave one arbitrary variable undefined, which we parameterize to find the minimum average normalized cost and mass. We also permute the materials used. Finally, for space sustainability, we use flake-resistant paint, which prevents the contamination of space by microdebris. In addition, ion propulsion thrusters are used for altitude control. I will now begin to discuss the financial section. We now have a very important question to answer. How much will this cost, and where can we get the money? Here is a table consisting of the costs of each component of the mission, from the launch to the communications fees. As you can see, due to the sheer amount of data that we're collecting, much of the cost is concentrated on communications. This comes up to about $10 million a year for communications alone. However, this is already quite a high estimate that we're using, and it assumes that we are handling all of the communications ourselves. There exist commercial satellite communication services that will very likely bring the prices down much lower. We aim to get this money from multiple sources, primarily governmental funding and venture capital programs. In Singapore, of note are the SSTL Space Accelerator Program, CapVista, and the Austin Space Technology Developmental Program. Additionally, by selling our data to commercial entities and other governmental agencies, we will also earn income that is used to increase the longevity of our mission.
In conclusion, our mission focuses on monitoring water-related climate change indicators as well as the Earth radiation budget to provide data. We also wish to monitor areas that are at risk of natural disasters such as tsunamis and flooding. This is done via multiple types of sensors built into multiple satellites, observing a large surface area of the Earth at once in different observation wavelengths. With Lachesis, scientists can then obtain a wider variety of data and make use of it to better fight climate change and respond to natural disasters. As people say, knowledge is power, and knowledge is exactly what we are providing.